Hello. We have been talking about finer points in compliant mechanisms after spending a lot of time discussing 6 different design methods for compliant mechanisms. One of the finer points we discussed is mechanical advantage in the last few lectures, and now and then we discussed bistable compliant mechanisms. The third finer point that we will discuss on related to compliant mechanisms is static balancing. This is a very important aspect for compliant mechanisms because whenever a compliant mechanism works, it has to work by elastically deforming. Elastic deformation is like a cut in the input energy, as we discussed in the case of mechanical advantage of compliant mechanisms is hampered by this necessary evil, if you call it. That is, necessary evil being that part of the input energy is used in deforming the compliant mechanism itself. After that cut is done, that is, there is input energy that is there, and then you use some of it to deform the mechanism to enable it to serve its function, and the remaining energy is what will be available at the output. So, this is a necessary evil, that is elastic deformation, which is essential for compliant mechanisms to work, but that also is a little sink in terms of energy. So, its mechanical advantage is affected, mechanical efficiency is affected, and one way to overcome that is to use preload, as we discussed earlier in the context of mechanical advantage, but now we will discuss another way which also in a way uses preload, but it is a concept of static balancing. So, we will look at static balancing in this lecture and then elaborate on how it could be used in the context of compliant mechanisms in the next 2 lectures. So, let us look at static balancing as a way to fix this necessary evil of compliant mechanisms, where part of the input energy is to be used to deform the elastic body of the compliant mechanism. It is a solution or a remedy for that, and that is static balancing. Let us look at static balancing of compliant mechanisms, and the first thing we have to understand is what is static balancing. Static balancing is when there is a load that can be a force or it can be a spring load. As you take the mechanism, a linkage mechanism, whatever, if you take it from position to position, will it stay in those positions? If it stays, then such a mechanism is called statically balanced. Okay. So, let us take an example to understand. Let us say that if there is a table lamp, okay, let us just draw a schematic of a table lamp. There is let us say a base here, and we have the lamp gives the light. Okay. This has some weight, and there is always gravity, we cannot escape that, right. So, I want to hold it at different heights. Now, when I hold it at different heights, will it stay there? It will not. In fact, if there is a table, if there are no static balancing features for this linkage, it will simply fall down and it will hit the table, but it stays. If you think of a table lamp that you would have used, wherever you put it, it will stay there. Sometimes people think that it is the friction in these joints that makes it stay where you want. It could, but we do not rely on that. Then usually either a counterweight is added, okay, some weight is added so that it will stay there, but then that weight has to be added for this. If it is only one lever, it would have been fine, but otherwise something else has to be connected, something has to be done to make it statically balanced, meaning that wherever I position this lamp, that is a weight, it should stay there. Okay. So, to contrast that, if I draw a cantilever beam, for that matter any beam, we take a simple cantilever beam. Okay. Now, I take this and deform it like this. Okay. In order to deform, I have to apply a force. Remove the force, it is going to come back. So, I will apply the force, it will be like this. The moment I remove it, it is going to go back, right, it will not stay. So, what will be statically balanced? If I take a cantilever beam, when I bend it, it will bend, and when I leave it, it will stay there, and then I bend it more, let us say it bends like this, it stays there when I remove the force. Is that possible? If that is possible, then we would say this cantilever beam is statically balanced. Okay, that is the idea. So, if I take a rigid body linkage, let us say I have just a link like that on a plane, if I rotate it, let us say something like this, it will stay. If there is no gravity, it will stay, but the moment there is gravity, and if this is the table, right, if I put it like this, it is going to fall back onto the table. How do I make it stay where it is when it has some weight or a mass, right? How do I do that? If I am able to do that, then I would say that system is statically balanced. So, if I have a abstraction like this, okay, let us say I have something like this, and there is a weight, constant weight, okay, irrespective of this angle theta. If I put it here, the weight will still act down like this, it should stay. Right now, when you put theta and there is a weight, it is just going to fall down, but we need to constrain it. How do I do that? If I am able to do that, then I would say such a thing is statically balanced. Basically, in all configurations of a mechanism, if it stays where it is without any external force, then it is statically balanced. That is important. So, that is, for example, the cantilever, as long as I apply the force, it will stay there, remove the force, it is going to come back. It should not be like that. Without external forces, the system should be in equilibrium by itself. When I say external force, W can be thought of as external force also, that is there, that is gravity balancing. Gravity load will be there, but no other force to hold it. If there is a lamp, as if I apply a force here, the weight force here both will be compensated, it will stay there, that is not the intent. The gravity loads can be there if it is gravity balancing, but no other forces. There should be something inherent in the system that will make it hold its configuration in any which way that you move it without having to put additional loads. Whatever gravity load is there, that will be there, and that should be compensated. If we do that, such a thing is called static balancing. So, this is the key reference for this work. It is a PhD thesis of Dr. Sangamesh Deepak in 2012 in Indian Institute of Science. Now, he is a professor at IIT Guwahati, and his thesis is very comprehensive. It talks about a lot of techniques for static balancing, both rigid body linkages as well as compliant mechanisms. So, when he was doing PhD thesis, it was realized by us that if you want to statically balance compliant mechanisms, first you have to understand rigid body linkage static balancing. Not everything was done, that is why he ended up doing a lot on rigid body static balancing and then extended some of it to compliant mechanisms. Why do you want to statically balance compliant mechanisms? As I said in the introduction to this lecture just now, that if a compliant mechanism is statically balanced, then there is no need for any external force to hold it in different configurations. That is, in any configuration, whatever input energy you give to it, all of it will be available at the output, because you do not need extra energy to move the mechanism from one configuration to another configuration, because statically balanced. If you have a compliant mechanism like a cantilever beam, if it is a spring or a beam or a mechanism, even if there is elastic deformation, you do not need energy to move from one position to another position, one configuration to another configuration. So, that is the advantage of compliant mechanisms if they are statically balanced. Then all the energy that is given to the compliant mechanism will be available at the output, just like rigid body linkages that do not have any friction in their joints. Then they are also perfect in terms of providing all the input energy at the output. Compliant mechanisms always there is a cut, part of the energy should be stored as strain energy inside the mechanism. Now we want to avoid that, that is why we want to do static balancing, that is what this PhD thesis considered. So, there are two ways to achieve static balancing of linkages in general. In this lecture we will talk about linkages, in the next two lectures we will talk about how to balance compliant mechanisms using what we discussed today. There are two ways to statically balance, one is called the counterweight, other is called the counter spring. So, counterweight, if I have an object such as this is the original weight, and as I turn this, I take this over here, wherever, if there is gravity, this is gravity balancing and there is gravity in this also. So, can I balance it? If I have a counterweight, that is this one, with a parallelogram linkage like this, it will actually be balanced, that is traditional way of doing. Okay. Now, in this particular case, instead of a counterweight, we have springs. These are the balancing springs. There are two balancing springs. Okay. So, this is other method, and this is good for compliant mechanisms, because compliant mechanisms are springs by themselves. So, when you want to balance a compliant mechanism statically, then using springs makes sense, because you can add a segment of a beam or two in order to imitate what these balancing springs do. So, it will become easy. So, both of these, as you move these original weights wherever you want, either the counterweight or counter springs will give you static balancing. We will focus on counter spring method, because that is more amenable for compliant mechanisms. A lot is done on counterweights, that is a well known concept. Now, spring will be more compact, and very innovative designs can be obtained with counter spring static balancing methods. The fundamental work in this is done by Lucien Lacoste way back in 1934, a long time ago. This Lacoste had done some very important work, but if you recall the title of his paper, it says a new type long period vertical seismograph, completely away from mechanisms, but in fact he relied on a mechanism in order to get very long time period vertical seismograph, more like a pendulum that moves very accurately, basically a very low stiffness pendulum, if you will. Okay. Any minute seismographic activity will be recorded by that. In the context of that, he came up with a very innovative idea, that is what we will discuss now. Let us say we have a rigid body, just like a length. Okay. Let us not about its mass. There is gravity, but we think this line does not have any mass, but there is a force acting here, constant force, that could be due to a weight. So, there is gravity and I put a weight like a big mass here, then this F is going to be equal to mg, where this mass is m. Let us say this angle is theta and this is the massless rod. Will it be statically balanced? Meaning, for any value of theta, if I put it there, it should stay there. Is that possible? What he came up with is that, okay, counterweight is always 1, but he wanted an alternative. Okay. So, what he did was he actually added a spring. Let me use a different color for it. So, he added a spring between 2 points, one point is anchored, other point is attached to this. Okay. There is a spring constant you took K, that is a linear spring, translational linear spring, and a height here from here to here, this height, let us call that h. Let us call this length where it is attached, let us call this b or something. Okay. Now, let us see what happens. What should be the values of b, h, k, so that this will be statically balanced, meaning wherever you position it, whatever the value of theta is, it should stay there. Okay. He did it in a different way than what we will be doing. Let us follow a simple method by writing the potential energy of this system, potential energy. In the last few lectures, when we talked about bistable phenomena, we said that minimum potential energy principle gives you stable equilibrium. So, when I take potential energy, the potential energy, if it has a minimum, it is stable, maximum unstable, and bistability we had taken, right. This is minimum, minimum, stable, stable, maximum, unstable. So, instead potential energy, if it is flat somewhere, that is neutrally stable, that is if it is flat like this, energy landscape is flat, you can position this ball wherever, it will stay there. That is exactly what static balancing is. Bistability was having minima and maxima going up and down, whereas static balancing means that potential energy is constant. In fact, strain energy is constant, because potential energy is strain energy plus work potential. According to the definition of static balancing, we said there should not be any external forces. Work potential is the negative of the work done by external forces, work done by external forces. So, in static balancing there should not be an external force. So, there is not there, it is equal to 0. So, potential energy is just strain energy, that is all there is, and that strain energy now has to be flat, meaning that whatever is the value of theta, if I were to plot this here, theta versus strain energy or potential energy, whichever way you look. Potential energy here in this case W, this force is there, so we can actually call it potential energy also. Okay. When there is gravity loading, later on we will be taking spring loads, then there is no potential, everything is strain energy. In this particular case, if you treat this as an external force, then this will be there. So, potential energy, which is negative of the external force, that will be there, work potential will be there, and we can take that. Let us write this. So, this potential energy in this case, for this example, it should be flat, meaning potential energy expression, if you write, that should not have a term that depends on theta, only then it will be flat like this. So, let us write potential energy for this. So, first let us write strain energy for it. Strain energy, we have a spring there. So, let us say half k into the length of this, okay, from there to there, if I call it L, L minus, let us say its free length, that is when there is no load on the spring, like your ballpoint pen spring will have a length when there is no load, that is when there is no load on it, that is when you are not stretching or compressing, it will have a length, that is the free length. L0 is the free length of the spring, free length of the spring. Okay. What is L here? L that we have indicated, that one. Let us use some trigonometry, so to speak. So, I need to know this length, okay, this let me use a different color. So, I need to know this, okay, different color I said, okay. I need to know this length and this length, then I will get that L. So, what is that length? If I call this B, that is going to be B cosine theta. Okay. So, L will be, if I use Pythagoras theorem, this square plus this square under root. So, under root B cosine theta square plus this length. So, we took care of this. What about that? That will be, the total was H minus B sin theta. So, H minus B sin theta square, that is our L. Okay. Let us remember this, go to the next slide. So, we can see what happens to the strain energy. So, L is B cosine theta square plus H minus B sin theta square. So, here L, let us write it again, that is B cosine theta square plus H minus B sin theta square, B sin theta square, that is our L. So, our strain energy here is half k L minus L0 square. So, I can write it as k by 2 into L square plus L0 square minus 2 L L0. Let us substitute for L square, then I get k by 2 L square is B square cosine square theta plus this square, we written that, and this one will be H square plus B square sin square theta minus 2BH sin theta, okay, that is L square, and then there will be L0 square minus 2L L0, that is your strain energy. And what is the work potential? Let us go back to the previous slide. This F, let us say this as the reference for that. Now, this height will be, if I take the length of this as L from here to here, that length is L, this will be L sin theta. So, L sin theta, that is the distance over which this force has moved, force is this way, it is going up. So, they are in opposite directions, and then work potential negative of the work done. So, it will be negative of negative positive. So, that will be mg L sin theta, because force and the displacement are in opposite directions. So, that is negative sign, work potential negative of the work done by negative of the work done is negative here. So, total positive. So, potential energy if I write, then I will get k by 2 for the strain energy part. There is B square cosine square theta, B square square theta, that makes it B square, and then I have H square, I have taken care of that, and then let us take care of these constants as well. Okay. So, I have L0 square minus 2 L L0, and then I have 2 BH sin theta, and then I have plus mgl sin theta, which is the work potential. Now, what are we saying? Potential energy has to be constant for all values of theta. So, one way to do this is, so I will write k by 2, B square is constant, H square is constant, L0 square is constant, L0 is constant, then I get this 2b what we had. Okay. So, when I have 2b sin theta, okay, and then I have mgl sin theta. In order to make it constant, the sin theta coefficient, this 2bk there and mgl. So, what I have, if I do not want it to depend on theta, then what I need to do is I will make 2 gets cancelled, minus bk, that is what I get here, plus mgl. Okay. This is what will multiply sin theta. If I do not want it to depend on theta, okay, I just need to make this thing 0, so that I will not have that those two terms at all. If I do this, if I choose my bk in such a way that bk is equal to mgl, that will become 0. So, what I end up will be k by 2 b square plus h square plus L0 minus 2 L L0. Okay. So, that is gone. So, now we have if I change the color, this term get cancelled, because I am making this to be 0. I need to satisfy that, that is bk should be equal to mgl. If I do that, then I will be fine. That is like a design. So, I go back, I have to choose the spring constant case as that that Bk equal to mgl is satisfied. Okay. Now, if you come back and look at it, these are all constant B, H and L0, but then this L is not, because if you see L, there is theta in it. What do you do? So, that is where this Lucien Lacoste's cleverness came. He said, let us make L0 0, right. So, is L0 0. What does it mean? L0 is the free length of the spring. If I have a spring, when there are no forces acting on it, that is L0, free length, okay, free length. The idea that Lucien Lacoste had was, let us make the free length 0. That looks nice. Then I have this and this go away, then I have potential energy constant, I have static balancing, but how do you achieve it in practice? He had ways of doing it also. 0 free length spring is one which has no force when its length is 0 and applies a force when its length is positive. That is, if I take a spring like this, it is a positive length spring, positive length spring. 0 length is something, if you really compress it there is a force. So, it should be a spring which has 0 free length, and then you can stretch it the way you want or compress it if you want, but something like this you cannot do, it is just 0 free length. It looks like a very radical concept. In fact, that is a radical concept. In fact, in his 1934 paper, he also talks about negative free length spring. This is positive free length spring. You can have negative free length springs and you can have 0 free length springs also. What does it mean? It means the following. If you have normal spring and a positive free length spring. Positive free length spring, if I say L0, L is its length at any time, L is the length, there is L0, it will go like this if it is a linear spring. A 0 free length spring will have a force characteristic like that, length is 0, it is 0. That is, if you connect the spring between 2 points, the force exerted is the spring constant times the distance between the 2 points, that is the 0 free length spring. That is not true here, because length you have to subtract L0. So, if I write positive free length spring, I write k times L minus L0, whereas here I would write k times L, that is a 0 free length spring. So, you can get such springs if you pre-tension them, that is, if it goes like this, this is a L0 here for a spring. If there is a pre-tension in the spring, such springs are available, then if you extrapolate it, okay, then it will go to 0 free length. Okay. Such, that is one way. There is another clever way, you do not need any special spring, you can take a normal springs and make them 0 free lengths. In this particular case, these springs are all 0 free lengths. How do you achieve it here? You see the diagram here, it exactly follows what is indicated there. So, there is this one and this one, and there is a spring here between these 2 points, there is a spring, but actually there is no spring. What you have is actually a string that goes like this and goes like this, and there is a spring attached here. Okay, there is a spring here. This is a positive free length spring, but there is a string attached. This is string, that is a spring, this is a string attached to this. There is a positive free length spring, there is string attached that goes over pulleys and comes like this. Okay. It is done in such a way that assembled in such a way that the force exerted here is proportional to this length. Let us see how it is done. It is done like this. You have a positive free length spring, and you take that positive free length spring, attach a string, inextensible string, presumably inextensible, you attach that and then you take it like this. Okay. Now, you position the pulley in such a way that this length is what you want here. That is what is shown, this x is x here. That means that when you bring it back here, it will go and the spring will not exert any force. Okay. The moment the string is long enough and you take it like this, whichever way you want, right, then the force proportional to kx. Okay, that is what we want. X is measured from here, there is no length when there is no force. Okay, that is how you can realize 0 free lengths in practice, and that is what is done for all the springs. The springs are here and then the string goes like this, spring here and then the string. Okay. So, between these 2 points from here to here we have a 0 free length. Similarly, between this point and this point, let me do with a different color. Between this point and this point there is a 0 free length spring that is attached to a string, and then there is a spring which is pivoted here. So, you can realize them using positive free length springs like this. Now, we move on to another concept. Can you balance one spring versus the other? That can be done. So, you have 2 springs, one of spring constant K1, other spring constant K2, here is a rigid part, okay, and this one will be balanced perfectly for any angle. So, one spring balance the other, it can be seen clearly. So, if I were to resolve the spring force, so if I look at this ADN, I can say dA vector d to a, that force, that is can be written as, I want to come from d to a, I can say I have d to n, d to n. So, I go like this and then come back n to a, or let us write it this way. Let us actually write it. The spring force, which is the spring force, okay, which is K2, if it is 0 free length spring, K2 dn, okay, d to n, or nd, whichever way. I can write it as summation of this an. I want to go from d to n, so I can say I can go to dA and then I can go to an. Okay. As a vector without K2 it is satisfied, so I can multiply K2 everywhere, meaning that the force of the spring, which is K2 dn, I can resolve in terms of dA and an. Likewise, the force of the second spring, the first spring here, can also be resolved as K1 AP from K1 AP, and then I have dA here, that will be the spring force here. Now, if I choose K1 K2 such that these two are equal, they are already opposite to each other, their magnitudes are equal, then the resultant goes through this and that will stay where it is because there is no torque. Okay. This way of working with forces is one way to do balancing, static balancing. It is a spring to spring balancing, one spring is balancing another spring. So, instead of that we can actually do this with energy method, which we just did for explaining Lucien-Lacoste's method. So, force way if you do, if I do not have 0 free length spring, instead I have positive free length spring, then this and this have to be made equal in all position, which is not possible because L1 and L2, that is length from P to D, that is L1, and D to N, that is L2, will not be the same in all positions of for various values of phi. So, they will not be statically balanced. So, the best way to do is you have to make it to be a 0 free length spring. If you make that, you can make these two equal in all positions. If it is 0, and if this is 0, L by L1 cancels and you have static balancing all the time. If you choose K1 AP is this length, okay, let us call this A, and let us call this AP, the length AP, and then this is AN, let us call this B. If K1 A is equal to K2 B, it is balanced provided we do not have this L01 and L02, okay, that is free length springs. If you have past free length, it will not be possible. So, spring to spring balancing can be done. It is an important concept because compliant mechanism can also be thought of as a spring. It may not be linear, but it is a spring nevertheless. Can you balance the compliant mechanism which is a spring with another spring? So, spring to spring balancing is what we are talking about here. So, this can be done with energy method if you will. So, we can do this. Let us say that I have pivots here, okay. So, let us say this length and this length. So, this length let us call it A, this length let us call it B. Now, I have some length let us call it L, and then now I put two springs, okay, both are, they have to be 0 free lengths, okay. Let us say I have this K1 and K2, okay. Let us call this length L1, this is length L2 in that position when I have this angle phi, okay. So, now let us write strain energy for, there are no forces here, that is the thing, it is not gravity balancing or force balancing, it is spring balancing, one spring balances the other. If I write strain energy here for the first spring, let us say half K1 L1, and there will be a free length for it L10 square, and then half K2 L2 and its free length square. Now, we will argue that unless L10 L20 are 0, strain energy in this case will not be constant for all values of phi. Where does phi lie? Phi will be there in L1. What is L1? If I use cosine rule for this triangle PAD, if I use that, then that will be A square plus that L square, that is L over there, A square plus L square minus 2AL cosine pi minus phi, that is this angle, okay, square root, that will be L1, and then L2 will be square root of B square plus L square minus 2BL cosine phi, that will be L1 and L2. Now, if you were to substitute here and then see, you will find that unless you make L1 0 and L2 0 0, you will not have static balancing possible here. So, another way to say that you need to have 0 free length spring. One more thing you will see is that there is cosine pi minus phi cosine phi. When you substitute here, when you expand this thing here, you would again find that if you want the strain energy to not depend on the angle phi, that is any configuration, strain energy should be the same, then the coefficient of this cosine phi that will come when you expand, that should be equal to 0. That will give you, because there is AL here, BL, L is common, there is A and multiplied by K1 there, and there is B multiplied by K2. What we said, that is K1 times A should be equal to K2 times B. They will have opposite signs because cosine pi minus phi is minus cosine phi, this is cosine phi, both have negative, but this will have negative cosine phi. So, in order to make this coefficient of cosine phi 0, we need to have K1 equal to K2P. So, energy method allows you to come up with the condition for static balancing. That is exactly what was there in Lucien Lacoste's work, and spring to spring balance also the same thing holds. This work was done by Professor Herder quite a bit. He is at Delft University. You can look up his papers where he has used this spring to spring balancing. Okay. Moving on, this is one of the things that Professor Herder had done. If you have 4 bar linkage, now you have a load here which is actually a spring load. this could very well be a compliant mechanism if you want to balance. That is what we will discuss in the next lecture. So, what Professor Herder did is added a number of springs and also additional bodies, right. So, original one did not have these two, he adds those and adds the balancing springs, okay. And auxiliary links are there, and this is the load spring, but he added 2 auxiliary bodies and 2 balancing springs, then he gets a static balancing for this. There is a method that he developed for that, okay. Here is the state of the art in static balancing of linkages with springs. First, if you have linkage, if there are forces like this, you can do this with counterweights or with the spring the way Lucien-Lefausse did. Okay. Here there is a force and there is a balancing spring. Now, here there is a spring load, there is a spring load and there is a balancing spring. That is a category 1 is force with counterweight force, and here spring with a force, here balancing spring to spring as we discussed. And as you take more and more complex linkages, this also becomes complex and you need to add additional bodies like it is done. These gray ones are the additional things that are added along with the springs. Whereas, is it possible to balance with springs alone? That was what was done by Dr. Sangamesh Deepak in his PhD thesis, and he also extended this. If I have a compliant mechanism like this, can we balance this by simply adding more springs to it? Meaning that can I add some flexible segments and get that. All those springs have to be 0 free length springs, that is why we talked about 0 free lengths here. So, just some of the thoughts here which we already saw this mechanism. If this is the load spring, for a linkage like this, he just adds 2 more springs, balancing springs like this, which are anchored to the frame like this, and all are 0 free length springs that will be balanced everywhere under this spring load. That is one thing he did. For a 2R linkage, he developed a general method for any linkage, or it can have a tree structured linkage. Now, there is one here and in branches of this way and that way and this way, and there can be spring loads more than once. What is the original load? There can be forces, there can be springs, then he would add these balancing springs. I will tick them with a different color. You have balancing springs, only balancing springs, no additional bodies, it can be done. He has a very important method that he did without using auxiliary bodies. You can look this up in this paper in Journal of Mechanisms and Robotics published in 2012. Perfect static balancing using only springs, but no bodies, no additional bodies. It has complicated figures like this in the paper, but you do not have to worry. All it does is whatever is in this table that you cannot see, if you have some configuration variables like theta, angles or sliding positions or whatever, coefficients of those variables have to be made 0 to make potential energy, or since there is no work potential, it will be just strain energy. For it to be constant, any dependence on the configuration variables like angles, sliding positions and so forth, those coefficients you make 0. That is the essence of it. Even though it may look very complicated, the essence that we discussed is exactly that. If you have expression for strain energy, potential energy written, then you make sure that coefficients of the terms that depend on the configuration variables, you make them 0, solve a set of equations, you get static balancing condition. Here is another reference where he had used the cognate. If you have 4 bar linkage, there are 2 other 4 bars that have cognates. If there is a spring load, his method actually said that if you statically balance 1 4 bar linkage, other 2 Roberts cognates can also be statically balanced. It is just a subtle result in his PhD thesis. To summarize, we discussed that static balance with a spring or with a few springs is possible, and for that you need 0 free length springs, that is the important thing. And if you use auxiliary bodies, that is what Professor Herder had done, and Herder's group. What Sangamesh Deepak did, what without using auxiliary bodies you can do that. In that the energy method is the key, which we discussed with 2 examples, the Lucien Lacoste's example with a force load or a spring load, both ways we discussed. Now in the next 2 lectures what we will do is we will use these concepts in order to statically balance a compliant mechanism. Thank you.